So we get to solving rational inequalities, and although there may look like a lot of things written on this page, there's really not a lot different from what we were doing. The only difference is worrying about asymptotes, because that's what we have with rational functions, so rational inequalities. Same idea, you want your function fraction on one side compared to 0. Now, the zeros of the numerator, those will behave just like what we were doing before with the polynomials. This function will be 0 if the numerator is 0. So if you have those inequalities that don't have the or equal to, we still want an open circle. If you have the inequalities that have the or equal to, you want a closed circle. Nothing changes there. Now, we know that in rational functions, the q of x gives us vertical asymptotes, which are important. Those are places, I'll say other places, where our function could change sign, could go from below to above or above to below. So we do need to keep track of them, but since they are not points where the graph is 0, notice what it says here. For the zeros of q of x, just always use an open dot. This is basically saying use an open dot for any vertical asymptote, right? They're not going to be points that are at 0, so we treat them like they're points that aren't at 0, that our function will not be 0 at those points. And so, using multiplicities, we already know the multiplicities rule for zeros of our function. The multiplicity rule for our asymptotes is, again, the idea of same infinities or opposite infinities. We saw that for the odd multiplicities, we had the opposite infinities. Well, in terms of opposite infinity, to us, what's important about that is it changes sign. It goes from down to up or up to down. So we're going to be going from one side of our x-axis to the other. So there will be a change in sign for all odd multiplicities. For even multiplicities of, again, our vertical asymptotes, there's no change because even multiplicities were that idea of same infinity, where both go up or both go down. So they're on the same side of the x-axis. So that's the rules for the multiplicities of our vertical asymptotes. I will say that we don't really bother sketching these like I was sketching the polynomial ones. Just follow the rules for open and closed dots and signs changing or not changing. That's what we're going to do. So our first example, already nicely factored for us. So we've got two things, right? We've got the x-intercepts up here. We've got vertical asymptotes down here. That's the biggest thing you got to pay attention to. Because for x-intercepts, if I just label those off here to the side, for the x-intercepts, that's coming from here. That's coming from the x plus 4 squared and the x minus 3. Okay? Let's allow focus here. There we go. So we're getting x plus 4 equals 0, x minus 3 equals 0. So we're getting negative 4 and getting positive 3. Now, this negative 4 has a multiplicity of 2. This one, multiplicity of 1. Okay, that'll be important. Now, over here, we'll look at our vertical asymptotes, which come from the denominator. X plus 1, x minus 2 cubed. So x plus 1 and x minus 2. I guess I should probably put that we're setting these equal to 0 technically. And so that gives me negative 1 and that gives me positive 2. This one coming from a factor that occurred once, so multiplicity 1. This one coming from a factor that occurred 3 times, so multiplicity 3. Okay? So there's our intercepts and asymptotes and multiplicities. Now, for our number line here, gotta get all of these numbers in order. Negative 4, 3, negative 1, and 2. So negative 4 would come first, then negative 1, then 2, then 3. I'm not worried about evenly or correctly spacing those numbers. Just get them in the right order. That's all that matters. Now, what's very important here, let's start with the intercepts where this or equal to makes a difference. This or equal to is telling you that these 2 points are places where the x value or the y value is 0. So at negative 4, we're on the x-axis. For positive 3, we're on the x-axis. And we want those points to be included if necessary. For these two, these are asymptotes. We do not have points on the x-axis here, so we definitely think of it as this is where your vertical lines are, your vertical asymptotes. So we're going to put open circles to signify there are not points at either of these locations. Okay, watch out, cat. Minnie's trying to invade the lecture here. All right, so filled in circles for those points because of the or equal to, open circles, always open circles because of the asymptotes. All right, now we need to find some starting point in here. Now this is the difference. With rational expressions, rational functions, we did not have a thing called end behavior. So we have to figure out a sign somewhere within this interval. Doesn't matter where. Normally, I'm going to say I almost always pick 0, as in if 0 is not one of these numbers, figure out where 0 is at. In this case, 0 would be a number between -1 and 2, right? We would have our 0 somewhere in here. Let's figure out what this function is at 0. Figure out its sign there. So plugging in 0 here, 0 plus 4 squared, 0 minus 3, 0 plus 1, and 0 minus 2 cubed. That's going to be 16 times -3. That'll be a 1. That's -2 cubed, -8. You actually don't even need to solve this. I'm going to, but you don't really need to. All you need to know is a sign. But we see this is going to be a -48 over a -8. And again, all that matters, negative over negative, is going to be a positive value, right? As soon as I see that, as soon as I realize that this is a positive number, right, that's all that matters. That tells me that if I plug in 0 into this function and get a positive number out, it's positive not only here, but for all the values in this interval. I know for a fact that I've got that sign in between those two values. So once you have one sign, you can actually work out from there in both directions. So let's work to the right. Working from this positive sign, going past the 2. So the 2 came from a vertical asymptote whose multiplicity was 3. And so that's another odd multiplicity. So both of these actually, odd multiplicities for asymptotes, that was the idea that we had the opposite infinities, or what we're going to really be concerned about here is changing sign, right? That's what an odd multiplicity means. Technically, whether you're talking about crossing or for an intercept or for infinities for an asymptote, any odd multiplicity is where you're going to see a change of sign, which means from positive, crossing past this point, again, that's the asymptote, on the other side, guaranteed it's negative. Now that we know this interval is negative, we hit our 3. 3 was an x-intercept with a 1, which you can definitely write the word cross here, or you can just state with the word change, because that's all that really matters. We know it's crossing, but what matters is an odd multiplicity is telling you that it's changing. I'm going to write both those words. It crosses, which means the sign changes, changing from negative back to positive. So we started there. We changed over that multiplicity of 3. We changed over that multiplicity of 1. That's where that's coming from. Now let's go to the left. Going to the left, we hit -1. -1 was, again, our vertical asymptote of multiplicity 1. So it's going to change from positive. Positive infinity will now be negative infinity. So it'll be negative in that interval. From that interval, hitting this -4. -4 was an x-intercept, but multiplicity of 2. So again, as an intercept, as a point, we know that is supposed to bounce for multiplicity of 2. What that means is we're going to have the same sign, right? The same sign on the other side. It's going to bounce here, coming from negative, bounce off, and still be negative. So I know I just did a lot there without really being able to completely visualize and graph them, but we're just following all of these multiplicity rules that we've known from before. Odd multiplicities, change sign. Even multiplicities, same sign. Whether you worry about it being a cross and a bounce or a, different infinities, same infinity, doesn't matter. Odd multiplicities, change sign. Even multiplicities, same sign. And with this graph of signs, we now finally get to go back and say, what do we want? We want less than or equal to 0. Okay? Less than or equal to 0 means we want all these negatives and to include points if necessary. So, starting from left to right, we've got negative. So we can start at negative infinity and come left. We hit this -4 and then bounce back down. So similar to the last problem, we want to include this, and we don't really stop. We just say it's negative, it's 0, okay, it's negative again. Not until we get to the -1 do we say, okay, now we're going to stop, because that's where it stops being negative, past this asymptote, now it's positive. So that describes all of that interval. And then we've got this small interval over here. So we'll union it with 2 that we don't want to include, up to the point when we get to 3, and then 3 being a point where it is equal to 0, we want to include, so we throw a bracket on that, and there's our interval for our answer.